Hello, everybody. Welcome. I'm Daniel Kane. I'm here to talk today about small covers for near zero sets of polynomials and learning latent variable models. This is all joint work with Ilias Diakonikolas. So where are we going to start? We're going to start by a very simple problem. We're going to try to learn Gaussian mixture models. So let X be a mixture of K spherical Gaussians in Rm. And by that, I mean you have K different means mu I, and what X does is it selects one of these at random according to some distribution, and then returns a random sample from the Gaussian centered at mu I with identity covariance matrix. And the problem is quite simple. Given sample access to such a mixture X, let's learn X. And so these sorts of mixtures of Gaussian models are some of the oldest and best studied latent variable models in all of statistics. And it is slightly more natural, perhaps, to consider mixtures of arbitrary Gaussians, where the covariance matrices can be whatever they want to be. However, in this case, there are m to the k-ish lower bounds, at least in the statistical query model. So for arbitrary mixtures, there are lower bounds, which makes it look like this problem is going to be hard, whereas for spherical Gaussians, no such lower bounds are known. Okay, so this is a problem, but what do we mean by learning X? Now, the strongest thing you might hope to do is do parameter estimation. Here, the goal is to estimate each mean mu I and each weight wi to error epsilon. And so there was actually progress on this problem a few years ago. Three groups sort of independently showed that as long as the minimum weight is at least alpha, and as long as the means are pairwise separated by about square root log 1 over alpha, then there are algorithms that do this parameter estimation in quasi-polynomial time. Now, the separation assumption is a little bit annoying. If that separation doesn't hold, these algorithms just don't work. But this is actually necessary for parameter estimation. So in particular, Regev and Vijayaragan proved that unless you assume some kind of similar separation assumption, then parameter estimation is actually impossible information theoretically to do in polynomial time. You can just polynomial number of samples aren't enough to identify the parameters to small error. Okay, so if we don't have this separation, what could we hope to do? Well, more generally, we could try and do density estimation. So we could try and learn some distribution x hat, such that the total variation distance between x and x hat is at most epsilon. And for this problem, information theoretically, it's actually possible. It was recently shown a couple years ago that essentially mk over epsilon squared samples is necessary and sufficient information theoretically speaking. But algorithmically, the best currently known algorithms have runtime that are exponential in k. So one of the things that we would like to try to do in this talk is see, can we close this gap, this basically exponential gap between our lower and upper bounds on this problem. And the general technique that we're going to be using for this is the method of moments. So you compute a bunch of low degree moments of x, and hopefully once you have those moments, you can use them to learn the distribution. So before we get into too much detail on this, we should ask ourselves, what are the low degree moments of this random variable? Well, for the expectation of x with probability wi, you get a sample from a component with mean mu I. And so the expectation should be just the sum of wi times mu I. Now, for the second moment, we need to know the second moment of this spherical Gaussian component. That you can compute to be mu I tends to the 2 plus the identity. And you note that all of those identity terms factor out. And this expectation is just the sum of wi mu I tends to the 2 plus the identity. And this identity term can sort of be canceled out, and you'll have just sort of this relatively nice expression in terms of the actual parameters. Now, something like this happens in general. If you want to learn the first d moments of the random variable x, that turns out to be basically equivalent to learning the first d parameter moments of x. That is the sum I going from 1 to k of wi times mu I to the tensor to the d. And basically, this is what your first d moments would be if you looked at the corresponding distribution just over the means of the components rather than sort of the actual Gaussian center of the components. And so you can compute the moments of this particular discrete distribution. Okay, so these are the moments we can hope to compute. We compute a few of them. How can we make use of them? And unfortunately, there is an obstacle to using these moments to learn our distribution. And in particular, their moments alone are not going to be enough. In particular, there exist two mixtures of k-spherical Gaussians, call them x and x prime. And even in one dimension, you can construct these families so that, firstly, the first k minus 1 moments of x agree with the corresponding moments of x prime. And secondly, the total variational distance between x and x prime is large. So you've got the red mixture here and the blue mixture, and their low order moments are the same. So you need to compute many moments in order to distinguish them. But they're very far apart from each other. These distributions aren't close. Now, in one dimension, this isn't so much of a problem. You can sort of avoid the method of moments and do something kind of exhaustive. You can, split the real line into little bins and then measure the probability in each bin and then just approximate by a piecewise constant function or something. However, you can take this one-dimensional example and embed it in higher dimensions. And in particular, if you take any line in higher dimensions and just along that line place centers of your Gaussians in exactly the same pattern we had before, we again find two mixtures of Gaussians now in m dimensions that match k minus 1 moments despite being far apart. And the problem now is that in order to distinguish these two distributions just from moments, you would need to compute k moments, which takes about m to the k time, which is too much. Okay, but it turns out that this particular example that I gave you was actually easy to solve. Because remember, we can compute the second moment matrix. This was, m, it's something like the sum I going from 1 to k of wi mu I transpose. And if you look at this, you'll note that the image of m is the span of the set of means. And so in this example, all of the means lie on a line. And so the span of all the means is one-dimensional or maybe two-dimensional subspace. You can figure out what that subspace is just from m. You can project everything down and you can solve it. Because once you're in 1 or 2 dimensions, again, there are exhaustive techniques that work perfectly well. So this sort of defeats that problem. And I will note that more generally, the image of m is always at most k-dimensional. And this actually is a pretty standard technique in this area, that you can take your mixture of k Gaussians and you can reduce it to a k-dimensional problem by looking at second moments. Okay, but we solved this particular hard example. Maybe there's another hard example that we can't defeat by any of those methods. And in fact, there is. Like this dimensional reduction technique only works when all of the means span a low dimensional subspace. And so if we can produce a case where that doesn't work, it's not very useful. So we're going to start with our low dimensional construction where things match moments. And then we're just going to add some noise. We take a bunch of components that we add to both x and x prime. And so we'll end up with something like a pair of mixtures of 2k Gaussians, such that firstly, x and x prime, they agree exactly on their first k moments. And secondly, if you look at the set of means of either of these distributions, they span a k-dimensional subspace. So dimensional reduction will only reduce you down to k dimensions, and then you'll need to compute k moments in order to distinguish which of these we're in, and that's impractical. So the question that we now have to ask ourselves is, how can we deal with an example that looks like this? And the point is that we can't, again, exactly identify x and x prime with a few moments, but we couldn't do that even when they all lie on the line. So maybe what we can expect to do here is we can identify all of these sort of noisy components that were added just to increase the dimension. And then after we've identified those, we can then identify this sort of critical line that passes through all the other means. So that's our goal. The question is, how do we do this? And to get a feel for that, let's take another look at this dimension reduction technique. So we have this matrix M, which is sum of Wi, mu I transpose. If you compute V transpose MV, this is the sum of Wi times V dot mu I squared. And you'll note that this is 0 if and only if V is orthogonal to mu I for all i's. Now, you can identify from M the subspace of all of these V's. And you'll note that since each mu implies only a single linear condition, this is a codimension K subspace. And we know that all of the mu's lie in the orthogonal complement to this subspace, which is some subspace of dimension at most K. And so that's sort of how this, this dimension reduction works. But how can we use this to maybe take advantage of higher degree moments? So suppose that we know the parameter moments of our distribution of all degrees up to 2D. What this allows us to do is it allows us, for any polynomial Q of degree at most 2D, we can compute the sum of Wi Q of mu I. And in particular, if we let Q be a square of some polynomial P, we get this quadratic form. Q of P is the sum of Wi P squared of mu I. And we note that Q of P is equal to 0 if and only if P vanishes on every single mu I. Now, this will hold. Now, I mean, each mu I gives only a linear constraint on these P's, so it holds on a codimension at most K subspace of the space of all degree D polynomials. And so we need to then figure out what we're going to do with this. So what we have is we have this vector space V of codimension K within the space of all degree D polynomials, such that we know that P of mu I is 0 for every polynomial in V and every one of our sample means. And so what do? Let's let V be the variety defined by the set V, the set of points where each of these polynomials vanishes exactly. And then what we're going to do is we know that every mu I is inside this variety V. But by some basic algebraic geometry, if you look at the space of degree D polynomials on V, that has dimension at most this codimension K. On the other hand, it is at least D plus the dimension of V, choose D. And so this implies that this variety V has dimension at most D times K to the 1 in D. And so as you increase D, the dimension of this variety gets substantially smaller. And hopefully, if we apply some sort of exhaustive algorithm, it should take time exponential in D times K to the 1 over D, rather than exponential in K. And I'll note that if you take D equals 1 here, you get V is exactly, it's a variety defined by a bunch of linear polynomials. It's a dimension K thing, so it's actually a subspace. When D becomes bigger than 1, the variety, the dimension will tend to drop, but the space that you get becomes a lot more complicated because, I mean, you're now defined by higher degree polynomials. Okay, so this is a good idea, but things are not very straightforward to make them work. I mean, there are a lot of problems here. Firstly, we can only compute these moments approximately. We can't exactly compute them, and so we can't exactly compute V. And so we get a bunch of polynomials on which all of our means almost vanish, but it's a lot harder to do some sort of algebra with that. But even ignoring that, I mean, computing V itself might be difficult. I mean, if you have a variety defined by linear polynomials, it's not too hard to compute the subspace that they define. But for higher degree polynomials, that's somewhat more difficult. But even if we did compute V, working on V is a lot more challenging. I mean, with the, again, with the subspace, we could project points onto the subspace and we could just reparameterize, and it would be the same as working on RK. But here, this more complicated thing, can we project on it efficiently? Do we know what that does to our distributions? Can we actually do computations with things valued in this variety? It's not clear. And finally, even if the dimension of V is small, that doesn't rule out it still being very complicated. Maybe the dimension of V is 1, but V itself is some sort of almost space-filling kind of curve, and the fact that you lie on this curve maybe isn't actually that useful. So there are a lot of problems, and it's hard to see how we're going to get out of this. But the basic idea is we're never going to want to work with V directly. Instead, we're going to find a cover of it. We're basically going to approximate V by a finite point set that we can compute. Okay, and so here's the thing that makes it all work. So proposition, let V be a subspace of codimension at most k within the set of all degree D polynomials in R. We've got some parameters, epsilon, R, and delta that have some relation. Then let's let S be the set of X and Rm so that the absolute value of X is at most R, and so that for every P in V, the absolute value of P of X, I'm not going to require that it's 0, but it's at most delta times the norm of P. So it's very small. Then I can cover X with epsilon balls, and the number of these balls is at most M, which is 2R over epsilon dkm to the O of D squared k to the 1 in D. And furthermore, not only does such a cover exist, I can actually compute it in poly M time. Okay, so this says, I have to restrict to a ball to make it work. I now have these polynomials only approximately vanishing, and I can find a cover that's not too big. So some notes. The dimension of V is at most D times k to the 1 in D. So you'd expect a cover of size about R over epsilon to the O of D k to the 1 in D. What we have is a little worse than that. We've got an extra D in the exponent. We've got some other polynomial factors in the base, but it's pretty good. Secondly, we have a requirement that delta is smaller than about epsilon to the D. And something like this is necessary to ensure that the width of the set S is not more than epsilon. If the set S had width more than epsilon, it'd be very hard to cover with epsilon balls. And finally, how do you prove something like this? Well, not easily. So the proof is entirely elementary. It uses facts from linear algebra and principal component analysis and things like that. It is, however, very involved, and we don't have time to go into it. If you're interested in the proof, look at the paper. Okay, so what do we do with this cover? So if we want to learn a mixture of spherical Gaussians, what do? We reduce the k dimensions by this dimension reduction thing. We do some clustering to reduce the case where all of the means lie in a ball of small radius. We let delta be some small number. We compute the first 2D moments of X to time the error. We then use that to compute the first 2D parameter moments of X. We use that to define this quadratic form Q, which is approximately the sum of Wi P of mu I squared. And you let V be the small span of the small eigenvalues of Q. Because you note that if Q of P is almost 0, then basically all of the means have to almost vanish at P. So we define S as we did before, and we get a cover C of size k over epsilon to the O of D squared k to the 1 in D. And we note that for each I, where the weight of that component, the ith component, is at least, say, epsilon over k, then mu I is within epsilon of some element of this cover. Okay, so we have a cover. How do we actually solve the problem? So for density estimation, we note that if you take all the means, all the important means, say, you can move them by only epsilon to get some mean in this cover. And if you translate all of those means like that, you'll note that our original distribution X is epsilon close in total variation distance to some mixture of spherical Gaussians whose means are elements of this cover. So what we have is we have an explicit set of probability distributions, and we have an X that we're promised is close to a mixture of these distributions, and we want to learn X. And it turns out that that problem is solvable. You can, in fact, just compute a maximum likelihood estimator for X using a linear program. And the upshot is we have an algorithm. It's polynomial in this cover size. But if you have a mixture of k spherical Gaussians in m dimensions, you can learn it to error epsilon. So you need poly m over epsilon time in samples to reduce to k dimensions. And then you need k over epsilon to the O of d squared k to the 1 d remaining. Note that if d is equal to log k, this is quasi-polynomial in k over epsilon. And this is substantially better because the previously the best known algorithms ran in time exponential in k. Okay, so what happens with parameter estimation? If we assume that this separation between the means, it's actually been known for a while, if you're given a cover C, there's a technique that allows you to cluster and use those clusters to do parameter estimation in time polynomial in the cover size. Since we know how to get a cover, we now immediately have an algorithm. The number of samples is poly m over epsilon plus k to the d. And the runtime is poly m over epsilon plus k to the O of d squared k to the 1 d. And well, if d is equal to log k, this recovers the existing results more or less. However, if we let d be somewhat smaller than that, we get a trade-off between sample complexity and runtime. If we take more samples, we require less runtime, and so on. And this sort of trade-off was achievable using the old techniques, but only if the separation between means scaled like k to the 1 in d. And this new technique allows us to get the same trade-off, but with only the sort of minimal square root log k separation. Okay, so that's learning mixtures of spherical Gaussians, but this technique is actually a lot more general than that. Basically what it says, you have for a latent variable problem, well, you learn the parameter moments. You then use our structural result to get this cover for the set of parameters. And then you run some algorithm that's sort of exhaustive in the cover size. And this seems to work on a lot of problems. In particular, we've got new results for learning positive linear combinations of ReLUs, learning mixtures of linear regressions, and learning mixtures of hyperplanes. And I'll briefly talk about the first two of those. So for sums of ReLUs, let's let f of x be a sum of ai times the maximum of 0 and x dot w, a ReLU function. In particular, I want ai to be non-negative for this to work. So your algorithm is given samples x, y, where x is a standard Gaussian, and y is f of x plus some independent errors. The goal is to learn an f tilde that approximates f in L2 distance. And previously, not a lot was known. So a result from this last year basically showed that the dimension reduction technique works. So you can get poly m over epsilon plus something exponential in k. But this cover technique handles it very straightforwardly, and we get a runtime that is poly m over epsilon plus quasi-polynomial in k. For mixtures of linear regressions, you have some beta i's in Rm, and you have some weights that add up to 1. Your algorithm gets samples x, y, where x is a standard Gaussian, and y is beta I dot x plus some noise, where which beta I you use is given by this probability distribution. So if it was just a single beta, this would be a linear regression, but instead we have a mixture of them. So the goal is, given these samples, you'd like to learn a distribution, the distribution x, y to small error. And there was some recent work on this. So Chen, Li, and Song solved a similar problem in time exponential in square root log k. And this improved on previous works that had runtimes exponential in k. However, we do substantially better. We have an algorithm that gets runtime basically quasi-polynomial in the parameters. Okay, so in summary, what did we do? We showed the existence of small covers for these sort of varieties or approximate varieties. This seems like it's the type of thing that algebraic geometers might be interested in. But we came at this from an algorithmic standpoint, and it gives us a new algorithmic technique for learning latent variable models using the method of moments. And in particular, using this technique, we got substantially improved algorithms for density estimation of mixtures of spherical Gaussians, learning positive linear combinations of ReLUs, and learning mixtures of linear regressions. So, thank you for listening. Have a good day.